Hey guys, my name is Annika and this is Chapter 9 of Physics, in which we'll be discussing heat. This chapter is going to have three main topics. The first is temperature and thermal equilibrium. Second, we'll look at methods for defining heat. And finally, we'll look at changes in temperature and phase. Let's start with temperature and thermal equilibrium. Chances are you've become familiar with temperature in the past, simply by coming into contact with objects that are either hot or cold to the touch. However, in physics, we're going to introduce some scientific methods that will provide exact measurements for temperature. The first thing to keep in mind when we're studying heat is that energy must be either added or removed to change the temperature of a substance. So, for instance, a substance can be heated by placing it in the oven and adding energy as heat, or it can be cooled by placing it in the refrigerator or freezer. Temperature is defined scientifically as the measure of the average kinetic energy of the particles in a substance. In other words, the kinetic energy that results from the particles moving around within a substance, as I've sort of drawn here on the right. We therefore know that temperature is proportional to kinetic energy. And a brief note, since the molecules in a substance can also rotate or vibrate, so they're not always moving around in a straight line, other forms of energy sometimes come into play, but we'll get into that later on with more complicated situations. There are a few basic energy forms that will be used in situations involving heat. The first is translational. This is similar to the kind of kinetic energy we've become familiar with in the past. This is just an object moving from point A to point B. So for example, this car that I've drawn, which is just moving from one specific point to another. The second is rotational. We got into this a little bit in the last chapter when we introduced torque. This describes an object spinning or rotating around its center of mass. And the final form of energy is vibrational. This is a little bit different. It has to do with the bending and stretching of bonds between atoms. So for example, plucking a string on a guitar. Those are the three forms of energy that will be used most commonly. When atoms move around within a substance, the resulting energy is known as internal energy. We define internal energy as energy that results from both the motion of the particles in a substance and the potential energy from the distance between them. So in other words, both what they're doing and how they're positioned within a substance. And here are some variables to describe internal energy. We express internal energy as simply a capital U, and then when there's a change in internal energy, we use delta U to show that change. When we're looking to measure and define temperature, a central concept is thermal equilibrium. This is a state in which two bodies in physical contact have the same temperature. Imagine dropping a hot pan into a sink full of cold water. You probably know from experience that over time the pan would cool down and the water would heat up a little bit as it receives heat from the pan. The same situation is true when using thermometers, which I've drawn below. This is the instrument for measuring temperature. If a thermometer is placed into a substance, such as the water I've drawn, the thermometer will eventually reach thermal equilibrium with the water, and that's what allows it to measure the temperature of the water. Another property that's essential to the thermometer is thermal expansion. As the temperature of an object increases, it will expand at a certain rate. And the coefficient of volume expansion determines how much an object will expand. So different objects expand differently under certain heat. So when a thermometer is placed into a warm or cold substance, the liquid inside the thermometer undergoes thermal expansion. This means it rises with increasing temperature to display a higher number of degrees. Thermometers are calculated and then labeled so that the thermal expansion of the substances inside them correspond to a certain number of degrees. Let's take a look at some units for temperature. The three most common units for temperature are Celsius, Fahrenheit, and Kelvin. If you're living in the United States, you've most likely become most familiar with Fahrenheit. This is the basic temperature we use for non-scientific purposes in the US. In terms of science, the most common forms of temperature are Celsius and Kelvin. Let's look at some conversions to help go between these forms of temperature more easily. To get from Fahrenheit to Celsius, we have the equation Fahrenheit, or F, equals 9/5, this can also be written as 1.8, times the temperature in Celsius plus 32. And this 32 is just the difference in freezing points between the two types of temperature. Secondly, we convert from kelvins to Celsius. A certain temperature measured in kelvins will equal the temperature in Celsius plus 273.15. And again, this is the difference in freezing points between the two types of measurement. And an important thing to note is that a change of 1 degree in Celsius will produce the same amount of change for that temperature measurement in kelvins. So in other words, if we have a certain temperature in Celsius, let's say it's 2 degrees, and we're trying to convert to kelvins, we'll add 273.15 to get 275.15 kelvins. If we increase the temperature in Celsius by 1 degree, still adding on the same factor, we'll end up with 1 degree greater in kelvins, 276.15 degrees. There's been an increase now of 1 degree on both sides. It would be slightly different if we were to do the same thing when converting from Celsius to Fahrenheit, because an increase of 1 degree Celsius would then be multiplied by 9/5 to create an increase of 9/5 degrees in Fahrenheit. So when we're studying these 3 units for temperature, some of the most important facts will be the ice points, or melting points, and the steam points, or boiling points, for each type of temperature measurement. So for Celsius, the ice point is 0 degrees and the steam point is 100 degrees. In Fahrenheit, if you multiply each of those values by 9/5 and add 32 to convert, you find that the ice point is 32 degrees, while the steam point is 212 degrees. Finally, in kelvins, the ice point is 273.15 degrees, and the steam point is 373.15 degrees. And as you can see, as I was explaining on the slide before, the difference in degrees Celsius between ice and steam, 100 degrees, is the same difference in kelvins. This is also 100 degrees. That's because the steps in each type of measurement system are the same. Now let's do some practice with temperature conversions. Number 1. The lowest temperature ever recorded on Earth is negative 128.6 degrees Fahrenheit. What is this temperature on the Celsius and Kelvin scales? So first let's go back to the equations that we learned previously in this section. We know that a temperature in Fahrenheit will equal 9/5 times its equivalent in Celsius plus 32. We also know that a temperature in kelvins will equal its equivalent in Celsius plus 273.15. These two equations are going to help us solve for these conversions. So first we'll solve for the temperature on the Celsius scale. If the lowest temperature in Fahrenheit is negative 128.6, then that will go on the Fahrenheit side. Negative 128.6. Over here, 9/5, we're solving for Celsius, and then we add 32. If we then subtract 32 from both sides to simplify, we get negative 160.6 equals 9/5 times the temperature in Celsius. Divide both sides by 9/5, and we're left with approximately negative 89.2 degrees Celsius. Now solving for kelvins will be easy once we know the Celsius value. If kelvins are equal to Celsius plus 273.15, we can take this value for Celsius and plug it in. We get the value in kelvins, negative 89.2 plus 273.15, or 183.9 degrees in kelvins. Number 2. You have a 102 degree fever. What is your temperature in Celsius? And this temperature is in Fahrenheit, the first 102 degrees. So we'll use the same conversion that we did in the last problem, where Fahrenheit is equal to 9/5 times the equivalent in Celsius plus 32. We know the temperature in Fahrenheit, that's 102 degrees. 9/5, we're solving for Celsius, and we're adding 32. So we'll subtract 32 to both sides, so it'll cancel out over here. We're left with 70 equals 9/5 times the temperature in Celsius. Divide both sides by 9/5, and the final temperature in Celsius is 38.9 degrees. Number 3. A hot pan is dropped in a tub of water. If the water's temperature increases, what will happen to the temperature of the pan? How will you know when the water and the pan will reach thermal equilibrium? So this problem, as you can probably tell, does not have any numbers involved. This is more of a conceptual question. And it's the same example that I used earlier in the chapter with a hot pan being dropped into cooler water. If we know that the water's temperature increases, that indicates that the pan did indeed start out warmer than the water. So the temperature of the pan must decrease to become closer to the temperature of the water. And once the temperature of the pan has decreased enough and the water has increased enough that the two are equal, that's how we know that the two have reached thermal equilibrium.